Good morning, welcome, and thank you for watching our 90% design presentation. We are Team Fish, students of St. Martin's University. Our project was provided by Thurston County Public Works using the geotechnical and survey data for a recent fish passage replacement at the intersection of Thompson Creek and Thompson Creek Road. My name is Edward Supis. I'm the superstructure designer of the bridge and assistant project manager.
My name is Jeffrey Lowe, and I focused on the hydraulics and the environmental aspects of this project.
Hello, I'm Abraham Dabasu. My role is Geotechnical Foundation and lead drafter for the SMU Fish Passage Senior Design Project.
The purpose of this project is the removal of the partial fish barrier at the intersection of Thompson Creek and Thompson Creek Road, which, if you see in the picture in the top right, is a squashed corrugated steel pipe. This project requires the design of a new river crossing structure, river improvement and regrading, and a river bypass for construction. Due to time constraint, the traffic detour planning was discussed but not pursued as part of our design and plan package.
Part of the environmental aspect of this project is the permits required for construction to begin, one of which is a stormwater pollution prevention plan, or SWIP. It is a customized, written strategy designed to be site-specific to identify potential sources of stormwater pollution. It details the best management practices employed to minimize pollutants in stormwater runoff from the site. It has been completed, but it is a living document and can be edited as the project progresses. To test the hydraulics of the proposed site, a combination of Civil 3D and HEC-RAS programs were used. Using the topography that was provided by the client, a post-excavation drawing was created using the 2-to-1 slope ratio grading that was agreed upon by the team. A reach of Thompson Creek was created using an alignment through the newly made stream bed profile, and sample lines were formed for the basis of the cross sections. This was then exported to HEC-RAS for analysis. The cross section shown here represents the water depth directly upstream from the newly removed culvert, using the 2-year flow information provided in a report from KPFF Consulting. There was no rain gauge data available, and there was no similar streams located near the site, so USGS regression equations were used to estimate the peak annual flow rates. 3 models were run using this data: a 2-year, 100-year, and even a 500-year, just for fun. This shows the cross section just below the construction site. According to a report done by Galder Associates, the average rainfall for the month of July is 0.8 inches in this area, but the 2-year analysis model was run in order to help predict the flow profile of a possible rain event during the summertime construction window. The 100-year water surface was used to determine if the proposed bridge height was adequate. The Washington Department of Fish and Wildlife recommends minimum freeboard of 3 feet below a bridge during such an event. And this profile shows that there is a 4-foot elevation difference between the existing road and the proposed creek surface below, so it's within the required specifications. The velocity of the new channel is also of great importance for the safety of the structure, as well as the future of the aquatic life inhabiting the stream bed. The results of the HEC-RAS modeling show that the velocities of the 3 stations shown in the previous slides are lower than the velocities in the existing culvert and are much closer to the average velocities of the stream as recorded by KPFF. Since the bridge channel velocities are close to the average stream velocity, some negative impacts that higher velocities could bring are not foreseen, such as scour or stream bed roughening. The 100-year model shows that the water is confined within the banks of the new channel, so there is no anticipated scour around the abutments of the proposed bridge either. Furthermore, since the average velocity of the proposed stream bed is close to the existing stream velocity, the migrating fish will have little trouble navigating the new passage unless there happens to be a flood event. The stream bypass originally proposed by our team was a pump and hose system. This concept was decided on due to the relatively short construction time projected for the project and the non-invasive setup. Due to the client's concerns over the constant surveillance needed, including overnight, to ensure that the pumps and generators do not malfunction, an alternative method is being proposed. Coffer dams will reroute the stream into a lined bypass channel that will be dug outside the construction zone. The 2-year peak flow will be used to help develop the new design of this bypass channel.
Moving on the first slide, it's the bridge footing type. The one difference I made from 60% to 90% is the footing type, which I picked spread footing for 60%, but I changed it into strip footing or continuous footing to 90% for several reasons. The first reason is uniform distributed load. Strip footing or continuous footing distribute the load of the bridge uniformly along the length of the foundation, and this helps in spreading the load over the large area, reducing the pressure on the underlying soil and minimum the risk of settlement. And the second reason is efficient use of material. Strip footing requires less concrete compared to spread footing, since they only need to cover the width of the bridge, piers, or abutment rather than the entire footprint of the structure. This makes them more cost effective and environmental friendly. And the third reason is ease of construction. Constructing strip footing is often simpler and easier than spread footing, especially in the area with limited access or challenging site condition. This can help reduce construction time and as well as cost. The fourth reason is the structural stability. Strip footing provides better lateral stability for a bridge piers, especially in the region prone to seismic active or a high wind load. The elongated shapes of strip footing resist horizontal force more effective than the spread footing. And the fifth reason is the foundation settlement, which is most important thing. A strip footing can better accommodate different settlement since they distribute the load over the large area, and this reduce or minimize the risk of structural damage or deformation caused by uneven seating of the foundation. On this slide, I would like to talk about the geotechnical and design analysis. Moving on the geotechnical and design analysis, my focus was on the calculations of footing to ensure the stability, proper load distribution, and enough soil bearing capacity. In this slide, I would like to discuss about the details of the footing design, being with the soil bearing pressure. The design observes a maximum allowable bearing pressure of 3 kSF, with the actual bearing pressure being comfortably below at 1.1 kSF, ensuring a strong foundation. The footing dimension and the wall thickness were determined to provide a capable support given the soil condition and the load requirement. I will also look at the load transfer, shear design, and reinforcement detail, all of which plays a significant role in maintaining structural integrity. The wall and the footing bearing strength ratio, as well as the bearing friction strength ratio exceeding minimum requirement. The reinforcement design, including the top and bottom bar, has been optimized to resist the moment and force exerted on the wall and footing. Moving to the material selection, I ensure that the concrete strength for both the wall and footing is at 6 KSI, while the reinforcement bar have a yield strength of 50 KSI for the dowel and for the footing rebar. These combinations of the material property contribute to the durability and load bearing capacity of the foundation. The stability check, covering overturning, sliding, and uplift shows factors of safety well above the minimum required. which indicates that the footing will remain stable under various load conditions, including the environmental load specific to the fish passage project. I will also conclude by discussing the applied load, including the axial force, moment, and shear force, both the service and the factored, and confirm that our design complies with the ACI 318-19 concrete design standard by considering each aspect of the footing design. I have ensured a foundation that will support the fish passage project's goals of ecological sustainability and longevity. On this slide, I will discuss about the footing design and calculation in detail. The footing design and calculation, the design parameters were established consider the soil bearing capacity, the geometry of the footing, and the load applied. I have observed ACI 318-19 design code ensure all our calculation meet industrial standard for safety and reliability. The footing width and thickness have been optimized to balance the soil cover and water table level, providing a strong foundation that maintains stability against overturning and sliding force. The detailed load analysis include service and forced load for axial force, moment, shear force, which are important for sizing our footing approximately. For overturning and sliding condition, the project environmental impact is reduced by the comprehensive analysis of potential overturning and sliding due to the lateral force. We have ensured that the safety factor for overturning and sliding exceeds the standard requirement, which is 1.5 respectively, and our calculations show that the footing resistance to those force is substantial, with the factor safety of 15.31 for overturning and 2.26 for sliding.
For the design of the superstructure, I would like to breeze through the material for an overview and introduction. For a deeper reading you can go to the structural plans and the design package that can be found in the link provided in the video description. The superstructure is primarily designed and checked through a LARSA 4D model that can check stresses and displacement. To verify the model's accuracy, its displacement and weight reactions were compared to calculated values. Note that AASHTO's LIFD bridge design specs were used for the model loads and load combinations. Both hand calculations and the model were subjected to a single line load, and it was found that the deflections were different by 0.07 inches, or 27% in the red circle, which I thought was good for this. In the top picture, both the concrete deck and the edge girder are on the same joint, but they are offset. This check was also to see if the geometry offset function of LARSA's modeling worked in regards to deflection calculations, which it seems to. The second verification was LARSA's material and section deadweight load, which turned out to be nearly identical to those projected by spreadsheet calculations in Excel. Note, steel member weights were pulled from AISC's Steel Shapes Excel database, which was copied as a sheet, so that then the yellow highlighted cell's shape can be input from a drop-down, and Excel's VLOOKUP function will pull out the shape's relevant properties. AISC's specification for structural steel buildings was the primary design code. The picture on the right shows the edge girder's shape properties, limiting weight to thickness ratios for compression and flexure, and a summary of the design checks utilizing a demand to capacity ratio. On the left is an example of one of the design checks, in this case, the moment capacity of a doubly symmetric I-shaped member in flexure. AISC was also used for the bolt connection design between the edge girder and the floor beams. Moment at the connection was distributed to the bolts as either tension or shear. Then the total tension and shear were checked in combination. In the connection plate, tear out and bearing, shear, and block shearing was checked. If you look at the picture at the very bottom right, which might be kind of blocked out, you see the red lines that show a potential rupture path. AASHTO's LIFD bridge design manual was only used for the elastomeric bearing pad design so far, which consisted of a check that the pad was large enough to accommodate potential movement, that the shear strains were okay, and that the pad was stable. Here's an overview of the bridge design. Note that there is no stabilizing member at the top of the arches. Following known effective arch ratios, it was found that the arch isn't high enough to accommodate trucks traveling below. It is possible to increase the height at the cost of good compression action, but this was chosen against, as the model showed the arches moved very little with the current member sizes and assuming a fixed connection to the edge girders. The framing plan is 8 floor beams at 17 feet and 3 inches long, spaced at 10 feet, for a total bridge length of 70 feet. This shows the layout of connections to the edge girder, which at present are the guardrails, cable connections to the arches, and the shear studs. All of them will be welded to the top of the girder. Whether this will be okay structurally for the guardrail and anchors are yet to be checked. Notice at the blue arrow, the longitudinal rebar to resist grout shrinkage and reinforce the connections is drawn in to confirm that everything fits. At the red arrow, the guardrail will be extended out by a wood block to allow clearance between the guardrail and the hanging cables and arches. This method of guardrail was chosen for its reduced weight in comparison to a concrete weighted barrier that could go further inward to give greater clearance, but the steel post method was easier to construct, it seemed. Here's the detail for the edge girder to floor beam connection, showing the bolt hole spacing, though we already talked about the bolt design previously. This is the floor beam to deck connection, utilizing bearing strips, hairpin rebar, longitudinal rebar, and shear studs. It does look like a tight fit, but seems to all fit and allow space for grouting. The floor beam strength is sufficient, and I would not like to increase the size to give more space if it isn't necessary. And the bottom picture shows the stud layout in the plan set. The arch connection is still yet to be designed. The two current ideas are as shown in the drawing, with welded plates to the top edge girder, or as in the picture to the right, a more encompassing concrete block to transfer the compression load. The connection for the cables is outlined as a clevis type of anchor still, but this has not been checked. Here are the outlines of the precast deck panels, currently set as 6 inches deep to span 10 feet in the transverse direction and 17 in the longitudinal direction. Design checks for the deck have also not been completed. As you see, the rebar is not drawn in yet. At a glance, we are behind schedule for the 90%, as there are still parts of the project that have yet to be designed and drawn out for the plan set. It is estimated to take another 2 or 3 weeks. A true 100% is not looking likely, but we still are on track to have the designs done and at least drawn out in CAD by the end of this semester. The cost estimate has increased slightly as more components were accounted for and the design costs were adjusted. The total project costs are estimated as $360,000, which still seems low for this scale of project, but hopefully this can be improved nearing the end of the semester and more of the design has been completed. The next phase is the 100% and finishing up design parts of the 90%, specifically the foundation plans and the deck and arch designs. The road grading also needs to be outlined, as it was found the bridge span is too close to the projected river flow height and may need to be raised by about half a foot or so. Note, the project is purely for educational purposes. The client has already begun construction and prepping for this project. Thank you for watching our presentation.